We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Hello everyone, I am Dr. SONAL MATHUR from AMIRAJ College of Engineering and Technology. Today we are going to talk about superconductivity. So students, till now you have studied about conductors, insulators and semiconductors. As we know that conductors are the material that conduct electricity very easily, insulators that don't conduct electricity, and the semiconductors whose resistivity is in between the conductors and insulators. Resistivity means that is the characteristic property of the substance due to which it opposes the flow of current through it. Right? Now, what is superconductor? The question becomes, what is superconductor? Superconductors, we define the superconductors as the material that lose their resistivity when they are cooled down below a certain temperature. Means the materials, they lose their resistivity on cooling down. Right? The materials can be cooled down by liquid nitrogen or liquid helium. Right? Now this phenomenon, to lose the resistivity on cooling down, this phenomenon is known as the superconductivity, and these materials that lose their resistivity are called as the superconductors. This phenomenon was discovered by the scientist Heike Kamerlingh-Onnes in 1911. For this research, he was awarded the Nobel Prize in Physics in 1913. He found that when pure mercury was placed in liquid helium, then mercury lost its resistivity at the temperature of 4.2 Kelvin, and the resistivity was found to be 10 raised to power minus 5 ohm centimeter, near about 0. Critical temperature, as we told that the superconductors are the material that lose their resistivity at a certain temperature. On cooling down, they lose their resistivity at certain temperature. Now the temperature at which these materials lose their resistivity is called the critical temperature. This is denoted by Tc. As we told that Kamerlingh-Onnes found that mercury lose their resistivity at the temperature of 4.2 Kelvin. So this 4.2 Kelvin is the critical temperature of mercury. The temperature at which the material lose their resistivity is known as the critical temperature, that is denoted by Tc. Now the question becomes, do all good conductors behave as superconductors? No. For example, like gold and silver, they are very good conductors at normal temperature. But when these materials are cooled down below a certain temperature, then they do not show superconductivity. Even some resistivity still remain in those materials. Now the resistivity that remains in those materials is known as the residual resistivity, which is denoted by rho naught. And the ceramic, which are insulators, that show superconductivity. So we cannot say the good conductors behave as a superconductor. Even an insulator can also behave as a superconductor. This is the graph between resistivity and temperature for superconductor and normal conductor. In this graph, you students, you can see that here for metal, for normal conductor, there is resistivity does not become 0. There is a resistivity that is highlighted by red pen here, rho naught, which is showing the residual resistivity. It's showing that on cooling down some resistivity remains in those material, which is called as the residual resistivity. And for the superconductor, you can see that at the critical temperature, that is denoted by Tc, the resistivity of superconductor is becoming 0. Right? So Tc is the critical temperature for a superconductor, and we can see here for the normal conductor, it is not 0, it is the residual resistivity rho naught. Now we are going to talk about some important properties of the superconductors. Some important properties are electrical resistance, persistent current, effect of magnetic field, Messner Effect, critical current, isotopic effect, impurity effect, pressure effect. Now we will discuss all these important properties one by one. So our first property is electrical resistance. Electrical resistance, as we saw in the definition also, as we told about superconductor, that the superconductor are the material that lose their resistivity on cooling down. At certain temperature, at the critical temperature, they lose their resistivity. So this is the property of superconductor, that the resistivity of superconductor drops to 10⁻⁻7 ohm meter at critical temperature. So we can say that virtually drops to 0. So ideally we can say that current should flow for infinite time through a loop of superconducting material. As they lose their resistivity, current should flow for the infinite time. Persistent current. The second property is persistent current. Persist means to remain inside, to remain for some time. So persistent current is when current flows through a superconductor, then it persists in the material even after the removal of source. Even after the that is, when we pass the current through a superconductor, then even after the removal of source, the current persists in the material for some time. Why this happens? It is because of the zero resistivity of material. Now the current that persists in the material is known as the persistent current. Okay. Now the third property is effect of magnetic field. In 1913, Camerling-Owens found that when a superconductor is kept in an external magnetic field, then as magnetic field increases, the superconductivity decreases, and at particular value of magnetic field, that is called as critical magnetic field, the superconductivity destroys. This critical magnetic field depends upon temperature. What is the critical magnetic field? Camerling-Owens found when a superconductor is placed in an external magnetic field. So when as magnetic field increases, the superconductivity decreases, and at particular magnetic field, the superconductivity is completely destroyed. Now the magnetic field at which the superconductivity is destroyed, that magnetic field is known as the critical magnetic field. Right? Now this critical magnetic field depends upon temperature, and this temperature dependence of the magnetic is given by the times equation. The formula, the equation is hct equal to hc naught in the bracket 1 minus T upon Tc ka whole square, where hct is what? Critical magnetic field at temperature T Kelvin, hc naught is critical magnetic field at temperature 0 Kelvin, and Tc is what? Critical temperature. Here you can see the graph between magnetic field, critical magnetic field and temperature. Right? After critical temperature, below the critical temperature, the material is in the superconducting state, and after the Tc, as the magnetic field increases, the superconductivity is destroyed and the material is coming to the normal state. Okay, so when the superconducting state, B equal to 0, and after Tc, after critical temperature, it is coming to the normal state. Next property is Messner Effect. Messner Effect is when superconductor is placed in an external magnetic field, then it expels all the magnetic field lines from it. This effect is called as the Messner Effect. Messner Effect means when superconductor is placed in an external magnetic field, then what happens? The material does not allow the magnetic field to pass through it. It expels all the magnetic field line from it. This effect is called as the Messner Effect. As you can see in the diagram here, when T is greater than Tc, the material is in the normal state. So all the magnetic field lines is passing through the material. But when T is less than Tc, less than critical temperature, then material is not allowing the magnetic field line to pass through it. It is expelling all the magnetic field lines through it. So this effect is known as the Messner Effect. Next property, critical current, which is denoted by IC. Critical current is what? When heavy current passes through the superconductor, then at particular value of current called critical current, the critical magnetic field also increases. Critical magnetic field means the value of the magnetic field at which the superconductivity is destroyed. Right? Now when current is passed through the material, heavy current is passed through the material, then at particular value of current, the critical magnetic field also increases. It destroys the superconductivity. It is obvious that when critical magnetic field increases, critical at the particular value of magnetic field, at the critical magnetic field, the superconductivity is destroyed. So when heavy current is passed, as we know that when current is passed, current and magnetic field are also related to each other. Current produces the magnetic field around it, right? When we are passing the current through the material, it is increasing the magnetic field, right? So when critical magnetic field increases, the superconductivity is destroyed. So at particular value of current, which is known as the critical current, critical magnetic field increases and it destroys the superconductivity. This effect is called as the Silsby effect. Now for a cylindrical wire of radius r, the critical current is given by IC equal to 2 pi r HC. Here IC is what? Critical current. R, radius of the cylindrical wire, and HC is what? Critical magnetic field. The next property is isotopic effect. Isotope means the elements that have different atomic mass due to difference in number of neutrons in their nuclei. Right? So according to observation, it was found that the critical temperature also varies with isotopic mass, and this relation is given by Tc is proportional to 1 upon root m. So we can see here that critical temperature is inversely proportional to the isotopic mass. So as isotopic mass will increase, the critical temperature will decrease. Now the next property is impurity effect. Impurity also affects the superconductivity. As impurity in the material increases, the critical temperature decreases. For example, pure mercury shows the superconductivity at 4.2 Kelvin, but impure mercury shows the superconductivity below 4.2 Kelvin. So we can say that the critical temperature also varies with the impurity also. As impurity will increase, the critical temperature will decrease. And the last property comes pressure effect. Some materials show superconductivity when they are placed under pressure. For example, cesium does not show superconductivity, but when it is placed under pressure of 110 kilobar, then it shows superconductivity. So we can say that at normal pressure, the material do not show superconductivity. When some certain amount of pressure is applied, then it starts to show the superconductivity state. So students, we discussed some properties of superconductivity today. Thank you.